Hello and welcome to another video on Joe's Physics Corner. Today we are going to talk about Feynman's last lecture, which is on the topic why are planetary orbits elliptical, which is basically the proof to Kepler's first law of planetary motion. What do we know already about planetary motion? Well, we learned in school that planets move in the form of a circle. So if this is maybe perhaps the sun, and we have the Earth here, we learn that the Earth travels in a circle, whereby the only force acting between the sun and the Earth, just gonna draw the vector for the Earth's force. We know that the force is equal to gmm over r squared, when we say that that's r, that distance. So this is what we know about planetary motion. We know that when the only force acting on the system is equal to gmm over r squared, and r squared here is important, that the force is inversely proportional to the square of the radius between the two objects, the distance between the two objects. When that's the case, we know that the planetary orbit would be in the form of a circle. But this is not true. In fact, perfectly circular orbits are nearly impossible, and even though it might exist, it's highly unlikely for two objects in space to move in the form of a complete circle. And then what is true? Well, what actually happens is, what Kepler has found out is that when there's the sun here, and when we draw the Earth's orbit is near to a complete circle. So the example I'm gonna take here is gonna be Halley's Comet. So when you look at Halley's Comet, it takes the form of a really radical ellipse, something that looks like this, even more radical, but for now I'm just gonna depict it like this. And what Kepler has found out is that planets that move in an elliptical orbit, in terms of regarding some central mass, which is one of the focus, Kepler has stated that there is another focus point. There are two focus points, one being the bigger mass, in which the comet or any planetary object orbits. One focus would be the big mass, and one focus would be just a focus point. And what they have stated is that the path that the comet takes is going to be in the form of an ellipse. Now, why is that? We learned from school that, well, if the only force acting from the comet to the object is gravity, which is given by gmm over r squared, we learned that it has to take the form of a circle, but that's not the case. And today I'm gonna walk you through step by step why that's not the case and why planetary orbits are indeed elliptical. And this is the first part of that video. It's going to be composed of, I believe, 4 or 5 parts, and this is the first part. And in this first part, I'm just gonna walk through a new way of drawing an ellipse. So what is the conventional way of drawing an ellipse? Well, the conventional way of drawing an ellipse is, firstly, we set 2 screws and two focuses on a piece of paper. And when you imagine this is a piece of paper, let's say we have 2 screws implanted into the paper. And what we do is, well, we have a string which is wrapped around the screw, and a pencil and a pen or pencil, and that string is tightened tautly so that there are no curves. Well, these are all straight lines. And this is where my pen is. And what we do is we basically stretch, we don't let these lines to get any curves. We make sure that they're all straight by increasing tension, by pulling my pen outwards. And what we do is we just trace the paths that it would take. And we know that this would be indeed in the form of an ellipse. And now what do we know? Well, firstly, because we know that the string has a constant length, and this here is also constant. This is a constant, and the total length of the string is also constant. We know that, well then, if we say that this is F1, focus 1, this is F2, focus 2, and this is any point P on the ellipse, we know that PF1 plus PF2 is also going to be a constant, because it's basically a constant total minus a constant. And so F1P plus F2P is equal to a constant. And that constant we call is equal to the focal sum, because they're basically the sum of the focal lengths from F1 and F2. Now this we all know. We all learned in school, how to draw an ellipse, and basically what it's telling us is this over here, that the length from any point on the ellipse to the 2 focuses, and then when we add the 2 values, we get a constant. And that's basically the definition of an ellipse. And now I'm gonna tell you another way of drawing an ellipse, which is gonna be crucial in proving why planetary orbits are elliptical in the next few videos. And so that way is to draw an ellipse in that way, we first need a circle. Let's say the circle has a center here, and what we're going to do is we're going to plot another point inside the circle. It will work basically anywhere inside the circle, but I'm just going to plot it somewhere over here. That's O, that's O, and I'm going to call that K. And K is called the eccentric point, or let's say E. E is the eccentric point. And what we're going to do is we're going to plot a line from E to any point on the circle. Anywhere on the circle. Let's say it's this line over here. And then what we're going to do is we're going to draw the perpendicular. First of all, I'm going to set that as P, this point here. And what I'm going to do is draw the perpendicular bisector of the line EP. Which means that, well, if that's going to be our midpoint, I'm going to label it M. And then I'm going to draw a perpendicular bisector, both this way and that way. And from this, up until now, what do we know? Well, because this is M is the perpendicular bisector of EP, we know that lines MP and lines ME are going to be of equal lengths. And then what we're going to do is we're going to draw a line directly from O to P. Now line OP, it's important to point out that this line is equal to the radius, because it's circle to any point on the circle, the center to any point of the circle, so it's the radius. And then if we draw a line, I'm going to label this as Q. If I draw a line from E to Q, I get this. now what do we know from these conditions over here? That first of all, OP is the radius, and PM is equal to ME. Well, we know that both angle PMQ and QME are right angles, and QM is shared, and PM and ME are equal lengths. Well, then it's a side angle side congruency, which means that the triangles QPM and QEM are congruent. And so these lengths here will also be of same lengths. Well, now then, what does that tell us? We said that OP is equal to the radius, and OP is composed of OQ plus QP. OQ plus QP. And here we just established that PQ is equal to QP. And so if you substitute this QP here with PQ, we get OQ here plus PQ is equal to OP, which is the radius. And we know that radius is always constant, whatever point P we choose. And so OQ, this length over here, OQ and QE is of constant length wherever we plot P. For example, let's say this time we plot P over here, over here. Say this P1 is our P2. You do the same thing, we join those two lines, those 2 points, and then I get the perpendicular bisector, which is about here. And we link P to O. And then we draw this line from Q2, now this is Q1, this is Q2, to E. And we get this is equal to that, and this is the radius, and this is also equal to that. And so line OP2 is now equal to line OQ2 plus Q2E. And so this plus this length plus this length is again conserved, and OP2 and OP1 are equal because they are both the radiuses of the circle. And so when we repeat this process from anywhere in P, what we will get is basically an ellipse that looks like this. There will be infinitely many triangles that goes like that. And an important thing to point out here is that although I've drawn like this, in fact what would happen is that the perpendicular bisector will not be going inside the ellipse. It will actually be tangential to the ellipse. So this will also be tangential. And so when we draw the infinitely many lines that links from P1, from O to P1, O to P2, O to P whatever, and we draw all those together, what we will get is a clear ellipse shape formed by the tangential lines that goes like that. And this form is important because what we will find out later on is that the velocities of the object rotating the central mass, the velocities will be shaped something like this. And what does that tell us? Well then, because the velocities are tangential to an ellipse, we can prove that the motion of things that are orbiting a central mass is going to be in the form of an ellipse. But that's for later. And for now, be familiar with this shape that we could somehow draw an ellipse by drawing countlessly many tangential lines that are formed by this simple geometry over here. Okay, so on to the next part. So now it's the second part of the video, and in this part of the video we're gonna prove Kepler's second law. And this is going to be important because it's gonna be the principle of Kepler's second law is gonna be used in my future derivations of explaining Feynman's last lecture, why planetary orbits are indeed elliptical. And if I say, if I'm gonna have to need the fact that planetary orbits are indeed elliptical to prove Kepler's second law, there will be no meaning. But what's good about Kepler's second law is that the principle doesn't really rely on the principle that planetary orbits are elliptical. It only relies on the fact that angular momentum is conserved. So I'm just gonna mention the principle of conservation of angular momentum, whereby it states that as long as there is no external torque acting on the system, angular momentum is conserved. So now how are we going to use this principle to prove Kepler's second law? Let's say there is a mass, a bigger mass like the sun, and a small mass here that we don't know whether its orbit is elliptical yet. We have no idea whether that's true. All we know is that due to the force acting between these two objects, there is some kind of velocity of this object traveling, we say velocity of v. Well then, what does Kepler's second law tell us? Kepler's second law states that the area swept by the motion of this object, it doesn't matter where this object is. When you measure the same time and measure the area swept in that same time, maybe a unit time, the area is going to be same wherever this object, this spinning, this rotating, this orbiting object is in terms of the big object. So for example, when it's here, or whether it's here and moving like that, when you measure the same amount of time, because it's going to be faster, well, it basically says that if the object is closer to the planet, to the bigger mass, it's going to travel with a greater velocity because the angle swept in that duration is going to have to be same. So I'm going to prove this principle by using the principle of conservation of angular momentum. So how do we get the area swept by this object? Well, let's draw let's say it's going to be, we're just assuming that this here is instantaneously at in a linear position. And so if we draw the area, it's going to look something like that. Something like that. The area swept by this object in this amount of time. And what do we know? It is in the form, as you can see, of a triangle. And in real life, it's not going to be in the form of a triangle. But what I'm going to say is that delta t is, this change in time. This, maybe I could say unit time, but not really unit time. This duration of time is so small, is a very small value. And for this, I could use, dt or whatever. But because I don't want to get involved with calculus, I'm just going to say it's a small change in t. So I'm going to say it's delta t, not dt, because I don't want to deal with calculus yet. Okay, so what do we know about getting the area of a triangle? Well, area is going to be 1/2 base times height. And what we know that the length of the base here is going to be radius, so r. And then what we have to know is the height over here, which is going to be a vector. Well, not really a vector. What we can see here is that this here, well, we could divide this vector here by two components. And what the component we are interested about here is the component that forms a right angle with the radius. Because when we're dealing with angular momentum, we have to multiply the the radius times the perpendicular velocity times the mass. And so the perpendicular velocity to this radius over here, so I'm going to say represent that as the vector of v perpendicular. So I'd say vp, yeah, vp. And then we know that the lengths, not the lengths, yeah, the lengths, I'd say the lengths here swept by this vector v would be in the same direction as vp because they're both perpendicular to the radius. And we know that this length here is velocity times time, and that time we have given is as delta t. We can say that this length over here is vp delta t. And so area is gonna be r vp delta t. That's gonna be our area. And now when we divide both sides by delta t, we get area over delta t. You can say it's a change in area because this is it would have an area here, and what we're dealing with is the area at this point minus area at this point. So it's basically a change in area. And so we're getting the change in area over the change in time is equal to r vp vector. Now, according to Kepler's second law, delta A over delta T, which is basically the area swept per a same change, small change or big change or whatever. Here I'm saying it's a small change. The area swept by this trajectory in a same given amount of time, same here is the important part, in the same given time is a constant, which means that this value here must be a constant. But what did we say about the principle of conservation of angular momentum? Well, the angular momentum, the total angular momentum in a system whereby there is no external torque acting on the system is constant. And here, is there external torque? No, the only force acting between the object here and I say the mass, the only force, so the only origin of torque, because torque, there must be a force for there to be a torque. And the only force acting between these two objects is gravity, which is given by gmm over r squared, f of g. And so because this force, f of g, is completely perpendicular to vp over here, we can say that there is no torque, there's no external torque acting on the system. And so angular momentum L, which is given by the radius, which is r, times the perpendicular component of velocity, so vp is equal to a constant. And so that's a constant, and we find the same value over here. And so that is also equal to a constant. And so we have basically proven that without assuming that the planetary orbit is indeed elliptical. Well, in real life, it's going to look something like that in the form of an ellipse. But without assuming that it is in the form of an ellipse, we have stated that the change in area over the change in time, so the area swept in the same amount given time, is going to be a constant due to principle of conservation of angular momentum. And now in the next part of the video, I'm going to use this principle to now solve or derive why planetary orbits are indeed elliptical. So on to the next part.